Math Humans. We're going to do 1.1 today. We're actually going to do a preview of calculus. There are three main topics in calculus, at least for Calc 1. We're going to be talking about the limit, the derivative, and the integral. So that's kind of cool. We only have three overarching topics to talk about. So the first one, the limit, and you've seen this in other math courses, but let's say I have a cute little function, and it has a vertical asymptote here and an asymptote here, and maybe the curves of the function look something like this. Well, if I want to talk the limit, I want to talk about what happens as a function approaches a certain value. So for example, if I want to talk about the limit of this function as x approaches 2 from the right. So let's talk about the notation. In theory, you've seen this in other courses. But this says as the function approaches 2 from the right, what is the function doing? And the function would be approaching a negative infinity. So then let's look at what happens to the function as x approaches 2 from the left. Remember, positive always means right, negative always means left. And if I look at this function, as I come in from the left-hand side, the function is approaching positive infinity. Okay? And then let's talk about what happens to the same function as x approaches infinity. So if we look at the very far extreme end of this graph, this function is going to be getting closer and closer to 0. So it's going to approach 0. And then what happens if I look at what happens as x approaches a negative infinity? Well, it's going to be approaching the same thing because this particular graph would appear to have a horizontal asymptote at y is equal to 0. So then let's talk about this guy over here. So what would be the limit of the function as x approaches a negative 2 from the left? Okay. Now, notice with the notation, it is important. Notice that I've written it this way. It has to be stacked. The notation is important. It has to look this way because this is the way that we communicate our math. Well, if I look at the function as x approaches negative 2 from the left, the function is approaching negative infinity. And then I'll do my last one, the limit of the function, as x approaches that asymptote now from the right-hand side, and it's going to approach positive infinity. So as I'm coming in from the right, the function is approaching positive infinity. So that's going to be the first thing that we talk about is the limit. And we will actually spend much of Chapter 1 working with limits. The next concept in calculus that we want to talk about are derivatives. Okay, and this is going to be the classic, the tangent line problem. Okay, and so here's what we're talking about. So let's say I have a cute little function, and maybe it looks like this, and I want to know what happens with a tangent line. So I have a tangent line to the curve at a specific point, and I have some ink blobbage. So if we talk about kind of the whole situation, for a line, the slope is constant for the whole line. And we've known that since Algebra 1, maybe even pre-algebra. So the slope of this line is consistent over the line. Well, if I have a curve, curves are a little bit different. They're a unique beast, and the slope is going to change at every point along a curve. So potentially, the slope is different at every single point along this curve. Well, the cool thing about the tangent line problem is I can approximate the slope of the function at this point by using a tangent line approximation. And we're going to talk around this, around and around and around and around. But we're going to approximate the slope of the curve, which is the derivative, at a given point, and oftentimes we can do that with a tangent line. So then a slight variation of that problem, okay, and this is usually how we approach this concept in the beginning, is so let's say this is my cute little curve, and I want to approximate the slope of the function, and I'm going to circle it so we know that that's our target at that point. Well, I could approximate with a secant line. So if I draw a secant line, so let's say I start out here and I draw a secant line. Well, the slope of the secant line is going to approximate the slope of the tangent line, which is also going to approximate the slope of the function. So I can actually draw a series of secant lines. So for my turquoise one, I'll scoot this up out of the way. I'm going to say the slope of secant 1 is going to be delta y over delta x. And so remember, these are my y values, and then this would be my delta x, okay? And that would give me one approximation. Well, let's say I chose points a little bit closer, and I drew that secant line. So the slope of the second secant line is still going to be delta y over delta x, but now if you'll notice, I'll do it down here and down here, my delta x is smaller, right? So in the original delta x, it went from here to here. Now my delta x has gotten smaller, and I'm going to try to stay on the same page, so I'm just going to squish it all in. Well, what if I take the slope of a third secant? It's still going to be delta y over delta x, but what if I make that delta x really, really close? So this would now be my delta x. Well, what we find out with calculus is as delta x goes to 0, then the slope of the tangent, because this would be this tangent line, is going to be almost exactly the same as the slope of the real tangent line, which is going to approximate the slope of the curve at that given point. So as delta x goes to 0, the slope of the secant is going to equal the slope of the tangent, which is going to equal the slope of the function. So it's actually kind of cool, and we will talk about this a lot in Chapter 1. All right, let me move us to a different page. The next problem in calculus is called the area problem. So far we've talked about the limit, and then we talked about the tangent line problem. Now we're going to talk about the area problem. So let's say I have a function, and the function does something like this, and I want to know what's the area under the curve from A to B. So if I want to find the area under the curve from A to B, that's just going to be an integral, which is actually kind of cool. And we will get to this in Chapter 4. So we won't actually start the third problem of calculus until we get to Chapter 4. Okay? So when we start talking about the area under a curve, we don't jump straight to calculus. We start by approximating by using a series of rectangles. So I can approximate the area under the curve, and I'm going to sum some rectangles, okay? Sometimes I can approximate the area under a curve by calculating different areas. And we'll talk about that in a little bit, but I would go back and use my geometry area formulas, and I will give you all of those again. But maybe I might approximate the area under a curve by something like this, and maybe this is the point A and this is the point B, and I want to calculate the area under a curve, I could do it by maybe doing a quarter of a circle, and then I would add it to a triangle. We'll call that triangle 1, and then I would add it to triangle 2, and then I could calculate the area under the curve from A to B. So sometimes we use geometry to help us with that, and actually I'm going to give you all those formulas today. But, so if we go back and look at the picture that we had before, derivatives, I'm going to do a derivative, and it's going to be s prime of x is equal to dy dx, and we're going to get that math starting in chapter 2. Okay, the limit problem is chapter 1, and we will do these throughout the year, but that's how we kind of introduce it. And then the integral problem is what we're going to start in chapter 3. So the next thing that I want to talk about before I give you all of your geometry formulas is slope. And remember that slope is represented often with an M. In calculus, we like to use subscripts to define what am I calculating the slope of. Is it the slope of the function? Maybe it's the slope of the tangent line. Okay, so I want to make sure that I always identify what I'm calculating. But slope is delta y over delta x, which is just the difference in the y's over the difference in the x's. This is also called a rate of change, and rate will become a lovely word that we manage throughout the year. Alrighty, so if we go back and look at our geometry formulas, so in theory, you know all of these. My assumption is that you have forgotten many of them, so I'm going to remind you of them, which means that from this point forward, you are responsible for that information. So the area of a rectangle is going to be the base times the height. The area of a triangle is 1/2 the base times the height. And then if you'll remember in pre-calc, we learned a glorious formula if you're given side angle side, and that is 1/2 the length of one side, the length of another side, the sine of the included angle. And remember that theta has to be the included angle. Okay. Alrighty, the area of a circle is going to be pi r squared. The circumference of a circle is 2 pi r. The area of a trapezoid, and remember a trapezoid looks kind of like this, okay? This is considered a base, this is B1, this is B2, and the height is the perpendicular distance between the two bases. So it's going to be 1/2 the height times the sum of the bases. Alrighty. The area of a parallelogram, and remember that a parallelogram looks like this. It has two sets of parallel sides, so this side and this side would be parallel, this side and this side are parallel, and basically it's just a rectangle that's been mushed, so it's base times height. Okay? So then I'm going to go ahead and give you some volume formulas just to make sure that you have them. So if I want to do the volume of a cylinder, and remember that would look like this. So I have a cute little cylinder, okay? It's going to be the area of the base times the height. And for most figures, the volume is always the same. It's the area, which is why it's a capital B times H. So this is the area of the base times the height. Well, the area of the base is a circle, so it's pi r squared H, okay? So let's say I want to do the volume of a prism. And for this particular case, let's say it's a square prism. So that's going to look like this. Here's my cute little guy, and he's going this way. Well, the volume, and I'll put this in here so we can see, oh, look how pretty that is still going to be the area of the base times the height. But if it's a square, and I think I forgot to give you that formula, so let's go back and say the area of a square is side squared. Okay, so then the volume becomes side squared times h. So it's really handy if you remember that the volume of any figure is the area of the base times the height. That being said, the volume of a cone, so let's say I have a cone, and this cone fits in here. So a cone, there are actually 3 of them per cylinder if I have the same radius and the same height. So it's 1/3 the area of the base times the height. Same thing for a pyramid, because basically it's just a glorified cone. The area of the base is different. It's still going to be 1/3 the area of the base times the height. And so if I had, can I draw that? Maybe I can. So let's say I have a base, and then here's my little top. Then here is my really ugly pyramid, but the volume is still going to just be 1/3 the base times the height. All right, my dears, that is it for today. Lucky you. I will see you soon.